1.6, we're going to chapter 1, section 6. We're going to solve radical equations. Okay? And when I say radical, I also mean rational exponents. Remember, the radicals can be written as rational exponents. That can help us in simplifying sometimes with this and doing that. First thing you want to do when you're trying to solve a equation that has a radical or a rational exponent is you want to isolate the radical or rational exponent part. That doesn't necessarily mean it's going to be the only part that has a variable. That's what we're going to run into here, is there's going to be some variables that are outside of the radical. We've got to get the radical by itself or the rational exponent part by itself. That's what we're trying to isolate here. So when we're looking at a problem, we're going to look at it and say, okay, this is the part I got to get by itself. So if it's not in this side, in this part, we're going to move it. Okay, so let's take an example to start off with, and we want to solve. Let's take x minus the square root of 4x plus 12. So, and it's equal to 0. Make it an easy one to start off with, so it's not equal to something really intense over there. All right, so if we want to isolate the radical part, which part is not inside of the radical? 4 points. The x on the front and this 0 over here. So if we could get this part away from this piece, away from that x, it would be isolated, right? Okay. We have two options. We can either move this x and then get rid of the negative, or we can just get rid of the negative by moving this entire piece here. Works the same. It mathematically is equivalent. One takes 2 steps, the others takes 1. I'm going to take the 1-step approach because they're subtracting this piece. If I add it back to both sides, it's going to cancel it out right there, and that's going to leave me x. What's 0 plus the square root of that stuff? It's that square root of that stuff, right? So that makes that the better option, I think, on this one. If there were a number over there other than 0, I would have moved the x and then divided by -1 because it would have been easier. We'll get to problems that we'll do that on as well. Okay, now the fun part. We get to solve this equation. Now, the second step after you isolate that radical part is get rid of it. What's the index? 2. So that means it's a square root. How do you undo a square root? Square. And if I square that side to get rid of the radical, what do I have to do to the other side? Square it. So whatever's on the other side, I'm going to square it. I put parentheses there. That's a good habit to get into because if there's something else over there, you need to put it in parentheses. So if you'll get in that habit of just always putting parentheses around that stuff, when you square it or cube it, whatever you do to get rid of the radical, if you'll get in that habit, it'll help you keep from making a small mistake that could cause big problems. Okay. Now, so that's going to give us x squared is equal to 4x plus 12. Okay. And that's a quadratic. What ways do we? It's a quadratic because we have x squared in the problem. If it's got x squared in the problem, that opens up a lot of different ways to solve. 3 that we've talked about a good bit in Math 100 and 110. In order to use factoring, quadratic formula, we've got to have that thing equal to what? 0. Okay, so we're going to get that equal to 0. I'm going to subtract 4x and subtract 12. I'm just going to do that in one step so that I get a 0 on that side. X squared minus 4x minus 12. Okay. Then I have the option of either solving by factoring or by completing squares and also an option, but we don't. That's a horrible way to solve them. It just takes forever. The quadratic formula or factoring is the way you'd want to do this. Okay, that I don't care which way you solve it. I'm going to do this one both ways to show you, to review both methods there. You understand that factoring doesn't always work, but quadratic formula will always work. So I a lot of times will just do quadratic formula just because I know it's going to work and I don't have to really think a whole lot about it. But this one is easy to factor, so that's why I want to show both ways. So let's do factoring first. If I do factoring, I'm going to use the X method. Something that multiplies to be negative 12 and adds to be negative 4. Negative 6 and positive 2. X minus 6, X plus 2 equals 0. Set each of those equal to 0. Get X equals 6 and X equals negative 2 as potential answers. Notice I said potential answers. It doesn't mean they are the answers. It means they're potential answers. They're the answers to that quadratic. That doesn't necessarily mean that they're answers to the radical equation we had at the beginning. Okay. If we did quadratic formula, x equals negative b plus or minus radical b squared minus 4ac divided by 2a. If we did that, it's the same result. Positive 4 plus or minus the square root of negative 4 squared minus 4 times 1 times negative 12 over 2 times 1. 4 plus or minus 16 minus or plus 48. 16 and 48 would be 64. 2 times 1 is 2. So that'd be 4 plus or minus 8 over 2. 4 plus 8 over 2 is 12 divided by 2 is 6. And 4 minus 8 over 2 is negative 2. Same two answers. Well, you got to be able to do both ways. Quadratic formula, if you're going to pick one way, you better pick quadratic formula because it always works. Factoring is not always an option. Okay. I'm showing this one both ways to review you on both methods for solving. You only got to do it one way. Okay. Now, we've got two answers. We need to check both of those in the original problem. Okay. One at a time. So I'm going to check, go back to the original problem. The original problem had x minus the square root of 4x plus 12. So I'm gonna plug in 6 first. 6 minus square root of 4 times 6 plus 12. I want to check to see, does that equal 0? That's what I'm checking for. Does it work in the problem? 6 minus 24 plus 12 be 36. What's the square root of 36? 6. Is 6 minus 6 0? That one works. So I know I'm keeping 6. It's possible that I'm keeping negative 2 as well. If I plug in negative 2 minus the square root of 4 times negative 2 plus 12, that'd be negative 2 minus negative 8 plus 12, which would be negative 2 minus the square root of 4. What's the square root of 4? 2. What's negative 2 minus 2? Nope. Negative 4. Not 0. That right there tells me that negative 2 is what's called an extraneous, N-E-O-U-S, extraneous solution. And I found it, but it doesn't work, so I throw it out. The only solution I have is 6. Positive 6 is the only correct solution that I have. I found 2 of them. I have to check them to make sure they work. Okay? And I showed checking by hand. I'm absolutely okay with you going into your calculator, typing in those numbers and getting it to work out there. You know, I showed how it was worked out there, but I wouldn't waste my time writing it out. I'd put it in the calculator most of the time. out of that. So, but it's called an extraneous solution if you get an answer and then it does not work in the original problem. It is possible for you to keep both answers or every answer you find. It is possible for you to throw one of the answers away and keep the others. It is also possible that none of the answers you find work and that you would have no solution to a problem because it's an equation. All of those three things could happen. We've had that happen in the past with equations. So all of those things are possible. The most common one you're going to have in here is you get answers and you either keep them all or you keep some and throw out one of them. Okay, that's the most common thing you're going to have. Okay, so let's look at some more examples of this. I'm going to more or less kind of example you to death on this stuff because it takes practice, lots of it. For this. All right, example B. Try not to skip a letter this time. Cubed root 5x squared minus 12x plus 6 minus the cubed root of x equals 0. This one is looks tricky, but it's actually easier because it has two cubed roots. I can isolate the bigger one, and then when I get rid of one of the cubed roots, what's going to happen to the other one? So if I move this little one here, if I move it by addition, that's just going to give me the cubed root of x right there. And the big one over here is isolated now, 5x squared minus 12x plus 6. I got a cubed root equal to a cubed root. How do I undo a cubed root? You cube both sides, right? We undid a square root by squaring. We undo a cubed root by cubing or raising it to the third power. And this third power and the cubed root cancel one another out so that we have 5x squared minus 12x plus 6 is equal to x. And again, it's a quadratic. It's got an exponent on the x, so we need to get it equal to what to solve? 0. So I'm going to subtract this x right here. And I'm going to subtract it to its like term on the other side. So that's going to give me 0 on that side. 5x squared minus 13x plus 6. So I've gotten rid of the roots or the radicals in the problem. And I noticed I had an x squared. Anytime you've got an x with an exponent on it, you need to get it equal to 0 to solve it. If you did not have an x with an exponent on it, all you got to do is solve it for x. Just get x by itself. But because we got an exponent on it, we got to get it equal to 0 and then use our other tools to solve. Okay, so tools to solve that. Quadratic formula or factoring. One of those two. Okay, this one works with either one. Remember, not always will you be able to factor, but you will always be able to do quadratic formula. Okay, so I'm a fan of quadratic formula because it always works. Okay, that doesn't necessarily mean that it's the easiest. Factoring works on this one; it's pretty easy, but quadratic formula also works. So let's do this in both ways, just to show you. Okay, if I'm going to do quadratic formula first, x equals 13 plus or minus negative 13 squared minus 4 times a times c divided by 2 times a. 13 plus or minus. I'm going to work out that number that's under the square root. So I got 13 squared, parentheses, negative 13 squared plus, minus 4 parentheses 5 6 parentheses 6. That's going to give me the 49 that's underneath the square root. 49. That works out real nice because we know the square root of 49. 7, right? So 13 plus or minus 7 over 10. So I got two answers. 13 plus 7 over 10. My brain is already doing that one. That's 2. That's one answer. And then 13 minus 7 over 10, which would be 3 over 5, because that's 6 over 10. Just 3 over 5. Yeah, by doing this stuff here, that's where the 49 came from. Do all the stuff that's under that there. So 3/5 and 2 are my solutions using quadratic formula. If you did factoring, you get the same thing. You did -10 and -3. So that'd give us 5x squared minus 10x minus 3x plus 6. Group 5x, x minus 2, -3, x minus 2. And then we get 5x minus 3 times x minus 2. And then it's going to get 5x minus 3 equals 0, which is where I get the x is 3/5. And x minus 2 equals 0 is where I get the x equals 2. Got two answers, and I need to check them to see if I'm going to keep both of them, throw out one of them, throw out both of them. Those are my options for this, okay? So I'm going to check 2, and then I'm going to check 3/5. 2 is easier to check in the original problem. So I'm going cube root of 5 times 2 squared minus 12 times 2 plus 6 minus the cube root of 2. We're going to see if that equals 0. This is what I'm going to do. I'm going to go to the calculator. I'm going to type that junk in because that's nasty to work out. So math, cube root, 5 parentheses 2, close parentheses, squared, minus 12 parentheses 2, plus 6. Get out of that cube root, minus, put another cube root in there, and then put a 2 in there. Hit enter. I had 0. Means it worked. 2 works. Now let's do the same thing, but instead of putting 2's in there, I'm going to put 3/5. Talk about nasty to work out without a calculator. And we want to see, does that equal 0? So the nice thing about the graphing calculator is you've already got a lot of that typed in. So I'm going to hit enter. And instead of a 2 there, I'm going to put 3 over 5. And then I'm going to go over here to this other part. Instead of a 2, I'm going to hit 3 over 5. And then I'm going to hit second insert, parentheses, plus. Get that back in there. And then over here, I'm going to delete that and then hit second insert 3 over 5. Here. And I get 0 as well. So it checks for both of these. That means I'm going to keep both answers. So our solutions, x equals 3/5 and x equals 2. Both answers work for this particular problem. Again, you don't have to do both ways of solving one. Pick one way. If you're going to only ever do one way, quadratic formula is the way you want to do it because it always works. But factoring is an option, but again, it's not always going to work. It's going to work quite often, but it's not always going to work. Quadratic formula will work every time if it's a quadratic to work with. All right. Let's do a tough one. It's a little harder. Let's see. Square root 3x plus 1 minus the square root of x plus 4 equals positive 1. So I'm putting a different number over there instead of just a 0, so that it's a little bit more interesting. Okay, so this one's got 2 square roots in it, but it doesn't have a 0 on the other side. So I can't just move that over there and get rid of it. I can move it over there to isolate one of the radicals. And that's what I want to do. I want to isolate one of the radicals, because if I isolate one of them, I can at least get rid of one of them and then do something else with the other one. So eventually I'm going to be able to get rid of both of them. But I'm going to start by doing this. That gets me the square root of 3x plus 1 equal to square root of x plus 4 plus 1. Okay. Now I'm going to square both sides to get rid of this radical, because it was an index of 2. Wasn't written there, so it's understood. Index of 2. On the left-hand side, I get 3x plus 1. That's the easy side. The other side, I've got the square root of x plus 4 plus 1 squared. What's it mean to square something? Multiply it by itself. So I really have this problem going on. Which is ugly and a little bit long. Not difficult, just a little bit long. Okay? Now, when I multiply that, it's like distributive property twice. So I'm distributing square root of x plus 4 to both pieces. So that's going to be square root of x plus 4 times the square root of x plus 4. If I think about just multiplying 2 of the square roots that are the same together, what's the square root of 7 times the square root of 7? It'd be the square root of 49, but it also is the square root of 7 squared, right? Which we know the square root of something squared is just the something back. When you multiply the square root of one thing times itself, the square root goes away, so that it's x plus 4 is that first piece. Square root of x plus 4 times the square root of x plus 4 gets me x plus 4. Technically, it's getting you the square root of x plus 4 squared, but the squared and the square root cancel each other out. Okay. So the next thing is square root of x plus 4 times 1, which is just the square root of x plus 4. And then we're multiplying by 1. There's another square root of x plus 4. And then 1 times 1, that's easy, that's 1. So that's going to get us x plus 5 plus 2 square root of x plus 4. I'm combining like terms there. Technically, there's a 1 in front of those square root of x plus 4, so that's why I put a 2 there, because there's 2 of them. It's kind of like counting them up. And then on the left side, I still got 3x plus 1. That hadn't changed. I finally brought that down. Now, can I get the radical that's in this problem by itself? How? Yeah, I can move this x by subtraction. I can move this 5 by subtraction. And that's going to give me 2x minus 4 equals 2 x radical x plus 4, because those pieces would be gone then. Could I get rid of that 2 that's on the front? How do I get rid of that 2? I can, but how? What's going on between the 2 and the radical? They're multiplying. The opposite of that would be divide. If I divide both sides by 2, that gets rid of it over there. So that's 2 divided by 2 is 1x. 4 divided by 2, 2. Well, that works out a little nicer. Now I have that second radical isolated. What do I do now? How do I get rid of the square root? I square again. So I'm squaring x minus 2. And on the right-hand side, that's the easy side. That's just x plus 4. On the left-hand side, squaring x minus 2 means x minus 2 times x minus 2. Which is going to give us x squared minus 4x plus 4 on that side. Takes a lot of algebra here to get to finally get to a problem that we can work. This is the problem we can work because we can get it equal to what? Why do we need to get it equal to 0? Why do we know we need to get it equal to 0 to solve it? It's right. It got to get it equal to 0. But why? What's the part in it that tells me I can't just get x by itself? What part of that problem says you got to have this equal to 0 before you start? The 2 on what? The x. This x squared tells me, hey, I got to get it equal to 0 before I start. If it did not have the x squared in it, I could just get x by itself and be done. Because it has x squared in it, I've got to do the work to get it equal to 0 first. Which this one actually ends up being really easy at this step. X squared minus 5x. The 4's cancel each other out. That's equal to 0. I wouldn't do quadratic formula on that one because it's too easy to factor. What do those two have in common? X. So x equals 0. X minus 5 equals 0. Well, there's one of my answers. My other answer is 5. The question is which one works, or do both of them work, or do neither of them work? How do I decide that? Check it back in the original. So if I check 0, I go back to the original, 3 times 0 plus 1 minus the square root of 0 plus 4. Does that equal 1? That's my question. 3 times 0 is 0. Plus 1 is 1. Square root of 1 is 1. What's the square root of 4? 2. Is 1 minus 2 1? No. So this guy is extraneous, so we throw it out. Okay? Check the 5. 3 times 5 plus 1. That'd be 16. What's the square root of 16? 4. 5 plus 4 is 9. What's the square root of 9? 3. 4 minus 3? 1. Checks. So the 5 is the one you keep. We found 2 answers. We checked them. 0 did not work. 5 worked. There are no rules that tell you you're always going to throw out zeros, you're always going to throw out negatives or anything like that. The only real rule is check it in the original problem and work it out. And it makes it work out. Those are fun. Let's look at some rational expressions with equations that have rational exponents. And I'll show you how those are actually easier. X to the 3 over 2 is equal to 216. We'll start with something really easy. Short or shorter, not necessarily easy, but shorter. If you've got a rational exponent, you can undo a rational exponent in a similar way that we undid the square roots or the cube roots. Think about a square root. What is it as an exponent? Square root turns into what power? The 1/2. And what did we do to each side to get rid of a square root? We squared it, right? 2 is the what to 1/2? Starts with an R. Reciprocal. So we were really using the reciprocal exponent for a square root. The reciprocal exponent for a square root is a 2. The reciprocal exponent for a cubed root is 3. So with a rational exponent, we can get rid of that rational exponent by using the reciprocal exponent. What's the exponent on the original problem? It's 3/2. The reciprocal exponent would be 2/3. So if I raise both sides to the 2/3, on the left-hand side where the x is at, 3 cancels 3, 2 cancels 2. That's just plain old x. On the right-hand side, I've got a number raised to a power. I can work that out. 216 raised to the 2/3 power, 36. Now that was pretty easy, right? Again, that was a shorter one. We're going to get to the ones that are longer. I did 216 raised to the 2/3 power. Just work that out. Let's do one that's a little tougher, but not a whole lot tougher. X plus 7 to the 2/5 equals 4. Is the part that has the rational exponent by itself. But the part that has that is by itself, right? There's nothing that on that same side that doesn't have the exponent, right? Right. So that means that part's isolated. So that means that I can go ahead and use the reciprocal power to get rid of that. I've got whatever I do to one side, I got to do to the other side. So I'm going to use, what power am I using? 5/2. It is that simple. This side, the exponents go away. There's x plus 7. 4 raised to the 5/2. Work it out. 4 raised to 5/2. 32. Now, can I get x by itself? Subtract 7. 32 minus 7 is 25. Here's the kicker. So what makes that seem too easy, right? This is what makes it more difficult on this particular type of problem. Look at the index of the power we introduced. What's the index of the 5/2 power? 2. The denominator was even. If the denominator is even on the power that you use, remember we had to do that absolute value thing? Absolute value takes into account the positive and the negative part, right? So not only do we have to work this problem, but we also need to work this problem. We've got, because of this even index, do positive and negative on that evaluation. And then, so we're doing x plus 7 is equal to negative 32. We would subtract 7 the same way and equal negative 39. And then we would go back and check that in the original problem. Remember, the original problem had 2/5 power there. So I need to check 25 plus 7 to the 2/5 power. 25 plus 7 raised to the 2/5 power. It's 4. And then I take negative 39 plus 7 raised to the 2/5 power. Does it equal 4? It does. So both of those work. I'm checking them just the same way that I did with the radicals in the problem, because technically these are still radicals, but they're just written with rational exponents. I really like using rational exponents better than I do roots, just because it's cleaner, it's easier, and it's quicker to write, in my opinion. Okay, takes a little practice. We're going to get some more practice as we go through the next couple of next section here with working some stuff. We're also going to solve some exponential functions with this. So let's do one more equation here and see if we can really put the nail in the coffin here. That's probably a bad analogy for math class, isn't it? So let's take x minus 3 to the 2/3 power plus 5 is equal to, let's do 13. What should be our first step for this problem? Why are we doing that? Joe, that's right. Yeah, to get the part that has the rational exponent by itself. So we're moving the 5 to get rid of the stuff that's not got a rational exponent. So that's going to give us x minus 3 to the 2/3 power is equal to 7. Right. 8, sorry. Too hard math, can't do subtraction, sorry. Now, can I get rid of the exponent? How? Flip it reciprocal power on both sides. So 3/2. That's going to give us x minus 3 is equal to 8 to the 3/2 power. 8 raised to the 3/2. All right, so it works out to be a decimal here. So we're not going to, I don't want to round that decimal till the very end. Okay, so I'm going to leave 8 to the 3/2 power in the problem. But because this has an even index, what kind of equations do I need? I need positive and negative on that. So I'm going to set up two equations. X minus 3 is equal to positive 8 to the 3/2. X minus 3 equals negative 8 to the 3/2. Both of them solve the same way. It's the same step to get x by itself on each one. You add 3. So that's going to give us x equals 8 to the 3/2 plus 3. And x equals 8 to the 3/2 minus 3. Or excuse me, negative 8 to the 3/2 minus 3. Those are the exact solutions. Now we can get the decimal equivalents for those. It should be plus a 3. Thank you. It's been a while since I've thought this one. Sorry. We'll blame daylight savings time. Yeah. I don't think that's the reason, but it'll work. So we could get the decimal approximations for those. 8 to the 3/2, 8 raised to the 3/2, and then plus 3, 25.63. Let's go 2 decimal places. And then this one would be negative 8 raised to the 3/2. Plus 3. negative 19.63. Oops, wrong. Negative 19.63. So those are the decimal approximations for that. And again, you could check those in the original problem and plug in those in. If you plug in the rounded decimal approximation, it's going to give you something really, really, really close to what it's equal to, which is what, 4 at the beginning. But if you use the exact ones, it'll give you the rates round. You're going to keep both of these. One way that you could keep the exact one and not get any rounded values, if you wanted to store something as x, I could do 8 raised to the 3 over 2 power plus 3. And if I want to store that as x, there's a button right here on the bottom left of your calculator that says STO. That's store. And then I can hit X and hit enter. And now anywhere I type an X on my calculator, on the regular calculator screen, it'll use that decimal unrounded. And so if I plug that into the original problem, X minus 3 to the 2/3 plus 5. Parentheses. X minus 3 raised to the 2/3 plus 5. 13. Is that the right? Did I write the right problem now? It is. And that's what's right. So that works. And then I do the same thing to store negative 8 raised to the 3 over 2 plus 3 and hit store as X. And now when I type in, if I just go back up here and grab this where I've already typed it and hit enter, it'll copy and paste it down there. And then I get 13 on that as well. But it's using X as this number now. After I've stored it as X, it changes it. It says, oh, now X means this. So that's a way of you get without having to type that number in over and over, because it gets, those exact numbers are always tough. But both of those work for that problem. Okay. All right. Last section of the night. Exponential functions. So we're going to go over to chapter 4.2 and talk about exponential functions. Spell it right. Exponential functions. Exponential functions. We talk about chapter 4. We're going to be in chapter 4 all week next week. All the lecture next week's come from chapter 4. So this is kind of the intro to that sort of stuff. So this will get us going for those things. There's 4 other sections that we'll talk about next week out of chapter 4. So I want to talk about exponential functions. Exponential functions basically are things that have a base and the variable is in the exponent. That's what makes it an exponential function. Exponential functions generally have a shape that looks something like this, or that's exponential growth. It's growth because it's going up and to the right. If it were going down and to the right, it would be decay, is what it's called. So this is exponential growth, and then this graph would be exponential decay. So growth would be like exponential. Things that grow exponentially are your money in a savings account grows exponentially. It may not seem like it does, but it does. The interest rate's so small right now that it stinks. So you don't get much money. But it is exponential in the way that it grows. Bacterial growth, it's a flu season. So that's exponential. You notice that when a lot of people have it, we turned out school in McNair County because of sickness, because we just had so many people catching the flu. It's because the growth of it was the attendance rate. If you tracked it out through a couple of weeks, it was steady, normal, and then it started curving. And once it got to a certain point, it really shot up. Our elementary school had about 230 out There's only 530 kids that go there, so it's almost half. So it's amazing how quick it grew to that. But it's all on exponential growth. Exponential decay. Have you ever heard of carbon dating for artifacts and things that they archaeologists find? That's exponential decay. They can calculate how old something is based on how many carbon atoms it's putting off, or estimate that. Ever how accurate you believe that is. It's still an example of exponential decay. My bank account is another example of exponential decay. It starts out here at the payday, and then about the day after that, it's down there at the zero button. So, but anyway, exponential growth goes up and to the right. Exponential decay goes down and to the right. Exponential functions have domains from negative infinity to positive infinity. All real numbers. The range is dependent upon the lowest value for the thing, but the domain is always that. Negative infinity to positive infinity. You can always count on that. If it's an exponential function, the domain is going to be that. If it is, the range is all going to be dependent upon what the equation is. It's going to have a flat, where it flattens out, it's going to be a point in which your range is going to start or stop. We will know that. So, but domain is always going to be this for exponential functions. Okay. Let's look at an example of an exponential function. Just play around with them a little bit. F of x equals 4 to the x. If we wanted to graph this, we could pick some x values and plug them in and make a table. If I started at -2, -1, 0, 1, and 2, I think that'd give us a good idea what's going on there. 4 to the -2 power, we know is 1 over 4 squared, which is 1/16. 4 to the -1 is 1/4. 4 to the 0 power, anything to the 0 power is 1. Okay. 4 to the first power, that's easy, that's 4. And then 4 to the second power, 16. Come on. Now, look how it exponentially grew. We started at 1/16, tiny amount. Within 1, 2, 3, 4 steps, we're all the way up to positive 16. So that's going from way down here to positive 16 really, really fast. That's exponential growth, right? So as we progress left to right, their x values, you get that. We can look at the graph of that on the graphing calculator. We've got that nice tool. So let's look at that. Hit y equals. And then we're going to type in 4, caret symbol. Put your x in there and hit graph. And you see that nice looking graph. It looks the exponential growth. It's flattening out here. What can we tell the range of this one is? 0 to infinity. This is going up. So we can look at that graph and help us get the where it flattens out is going to be the bottom part, or for this one, since it's going up, it's going to be the bottom part of your range, and it goes up to positive. So we can use that graph to help us do that. Let's look at another one. Example B. Let's do f of x is equal to 1/2 to the x power. 1/2. Put the fraction in there. Let's do the same idea. If I use -2, -1, 0, 1, 2. If I raise 1/2 to the -2 power, that's going to be flip the 1/2 squared, so it's going to be 4. -1 power is going to be 2. Anything to the 0 power is 1, and then 1/2 to the 1 power is 1/2. 1/2 squared is 1/4. We see moving left to right with the x values, we're starting up at 4, and then as we move this way, it's going down to 1/4 small amount. So we start up here at 4 and go that. Doesn't decay as fast as the 4 as the base does, depending on what the denominator of your fraction is, how fast it will decay. The bigger that number is when it's a 1 over fraction or unit fraction like that. If we look at the graph of that, when you put that in there, you want to put parentheses 1/2, close the parentheses, raised to the x to get that to graph. And when you look at that, notice here at -2, that's where we're at 4. At -1, we're at 2. At 0, we're at 1. At 1, that's about 1/2. You can see it going down there. What would the range of this one be? What's the lowest point on the graph? 0. What's the highest point? Infinity. So it would still be from 0 to infinity. Even though it's turned around, looks like it's turned around backwards, it's still going up that way. Okay. What would make it turn where the highest point of your graph would be that? Let's look at one of those. Let's say we had f of x is equal to negative and then 2 to the x. Let's look at the graph of that. We won't worry about building a table for it. If I just put that into my calculator, negative parentheses 2 raised to the x. Just type it in exactly. So that flips it over. And now this one would be from negative infinity up to 0. So that's what can flip it over that way. Okay. That negative on the front does that to it. Okay. Domain is always negative infinity to positive infinity. Range, look at the graph. And that's going to help you get the right places there on those. Okay. Let's look at another one. Again, we're looking at domain and range of these things. Let's say we had y is equal to 3 to the x and then minus 2. Or let me write it f of x. That's the way we're writing here. Think about transformations that we did over the course of the course. What does subtracting 2 on the outside do to the graph? Drops it down 2, right? So we should see this exponential. This one is similar. It's not going to be as fast growing as the 4 to the x thing, but it's going to look similar to that. So it's going to start here flat and go up, but it's going to shift down 2 units. So our range is going to change. If we look at the graph of that, about triple that. Catch my death up here. So if I look at the graph of that, y equals, and then clear that one out, 3 raised to the x, and then minus 2. You see that graph, and you see how it shifted down. So what the range of this one would be what? Negative 2 to infinity out of that. So we can see that how that changes things. If you add something on the outside of that, it's going to shift it up that many units. Subtracting on the outside shifts it down. All of those same things still apply here. We're not doing anything different as far as that goes. Keep in mind, anytime they're asking you about a function, you can graph and see what's going on. Most of the time, you'll be able to answer any question about a function by looking at its graph. So that's what I want you to do with those particular types of problems. Look at the graph. That'll help you get the range. The domain's always going to be negative infinity to positive infinity. You don't have to think about that. But the range, the graph's going to tell you everything you need to know about that. So be able to look at that graph and do that. All right, let's get into solving some exponential equations that are. This is a little bit different solving than what we were doing. It's not quite as intense, which is a good thing. So we're going to end on a somewhat easier thing than what we started with for as far as solving equations going. So let's look at that stuff. So we're going to solve some exponential equations. Not rational exponents, just exponential. Okay? So What letter are we on here? I'll skip letters this time. E. 5 to the x equals 125. All right. Here, it's exponential equation because the variable is in the exponent. That's what makes an exponential equation. Okay? One of the strategies for solving exponential equations is to think about rewriting each side with the same base. What's the base of the side that has the exponent? 5. Can I rewrite 25 as 5 to a power?
Yeah.
How? It becomes 5 to the third. So we have 5 to the x is equal to 5 to the third. The reason it becomes 5 to the third is because I know 125 is, what, 5 quarters? 5 times 25, and that's 5, 5. So there's 3 5, so it's 5 to the third. If the bases are the same, you got 5 to the x, and this is 5 to the third. What does x have to equal? 3. That's it. X equals 3. You're done. The reason you're done is because x is already by itself. And we get that easy equation to do. Let's look at a harder one. 3 to the x is equal to 27. Again, name of the game. Get the base the same. Get the base the same and work. 27 is 3 to the third. So what does x have to be? 3. Let's make it a little tougher. 2 to the 3x is equal to 32. Look at the base on the side that has the exponent. It's 2. 32 is what? That's 2. So that's 16 and 2, 8 and 2, 4 and 2, 2 and 2 again. 1, 2, 3, 4, 5. 2 to the 5th. Okay, this one's not as straightforward. I got the bases the same, but it's got 3x. So how do I set up my equation? The bases are the same. Look up here. I did 5 to the x is equal to 5 to the third, and my equation was x equals 3. I didn't have to do anything because there's x was by itself. Here, what would my equation be? 3x equals 5. Good job. And then I can solve that. I set up the equation 3x equals 5 and get x by itself. 5/3. That's okay. Let's try this one. 3 to the 4x is equal to 243. It's a weird number, but I've got to think because the base on the left side's a 3, that 243's got to be 3 to a power, most likely. Three times 81 is 243. 81 would be 9 times 9. 3 to the 5th power. I'm asking you. Yes, it's 3 to the 5th. That's right. Now, what's my equation that I set up? 4x equals 5. Get x by itself. Yeah. 3 to the x plus 1 equals 9 to the x. Get a little tougher here. And x on both sides. Which one of those bases could be changed? the 9, right?
Well, on the right.
9 could be written as
3. No.
3 to the second power, right?
Yeah.
What's the rule for these two exponents? It's parentheses and an exponent on the outside. You do what with the exponents on the inside? Multiply. 2 times x would be 2x, right? So this is really just 3 to the 2x. Now the bases are the same. What's my equation that I set up? Good job. X plus 1 equals 2x. The bases are the same. They go away, and you just get the exponent as your equation. Okay. Now we can just get x by itself here. Subtract x. 1 is equal to 2x minus 1x is x. X is equal to 1. Do a tougher one. We always have a little bit of trouble with this one because they want to think about in terms of multiples and not in terms of exponentials. What do we know about 4 and 8?
Hey, what we're doing.
2 times 4 is 8. But 4 is also 2 times 2, isn't it? 8 could be written as 2 to what power?
Third power.
Third power. 4 could be written as 2 to the second power. That would get the bases to be the same. So I could have this 2 squared to the x plus 5. And write this as 2 cubed to the x minus 1. Again, what's the rule for exponents when you've got parentheses and an exponent outside? You times it. 2 times x plus 5.
2x plus 10.
2 to the 2x plus 10. And on the other side, we get 2 to the 3x minus 3. What's my equation that I set up?
2x plus 10. Get x on one.
Yeah, get x on one side. I'm going to subtract 2x, and I'm going to add 3. So there's 13 and x. X is equal to 13. Okay. Again, this is much easier than the previous sections about solving equations. Exponential equations are not too difficult. You want to make sure, though, that you're getting the bases the same. We're going to learn some skills next week where what if you can't get the bases the same? Every one of them you'll do this week, the bases can be made the same. So that's the way you want to do that. All right. So last thing we got to deal with is some money problems. We're going to deal with some money problems. We all got money problems. No matter how rich you are, you got money problems. Too little or too much. I know which one I fall into. But yeah. I play music with a guy that is too much money kind of problem. Yeah, exactly. That's what I say every time I see him. Must be nice. But he works hard for it, so
Yeah.
I would not want to deal. I deal with a lot of stress every day. I wouldn't want to do this. He's the what's the person right underneath the CEO? What that
The CFO.
Yeah.
Chief Financial Officer.
Of Bancorp South. So.
You got a headache.
Yeah, he's got hot headaches. I'm sure. So when we get together, we usually don't talk. Thank you. So here, this formula is the key to being able to do this stuff. So what we're going to be doing is some compound interest the formula, the things that you're finding here or that you're plugging in, that P is the principal investment. That's how much money you put into the account to begin with. Okay? R is your interest rate. N is the number of times it's compounded. And then T is time in years. Always in years. You do with finance, you do with years. A is just account worth, is what that means. Okay, so principal, investments, how much you put in the account to begin with. R is what the interest rate is. N is the number of times it compounds. So we talk about the number of times it's compounding. So like your normal savings account is a quarterly account, which means it compounds 4 times a year, quarterly, once every quarter, every 3 months. So some savings accounts or funds will compound interest monthly. Kind of hard to find a local bank that'll do that, but some of the national banks that you can do online will do monthly. Some of the accounts will compound interest daily, even. Those exist. They're hard to find. You almost have to have a really, really large amount of money to put into it for them to, there's a really large minimum balance that you have to maintain for that kind of account. And semi-annually would be how many times a year? 2 times. And then monthly would be how many times?
12.
Bi-monthly would be 6, that sort of thing. All those things, yeah, quarterly's 4, semi-annually's 2, daily's 365. And then you could do hourly, I guess, but I don't know if you're ever going to find that. But in theory, those things could happen, okay? So and then the number of years, if they told us 6 months, the number of years would be 1/2. Okay, so we're always dealing with years, so you got to convert into years, no matter what, for that formula to be in the right thing. So let's start out with the easiest of the problems, and that would be one where we invest $2,500 into an account. Yes. Drawing. Let's say we're back in the 80s, and the interest rate is 6%. That's a really good interest rate, but also you got to keep in mind the borrowing interest rate is probably twice that. Which is, right now the borrowing interest rate is for home loans is in the 3 to 5% range, somewhere in between there, depending on when you catch it. Car loans, it's it's just all over the place. They really don't have any regulation to them as much as home loans do. But savings account interest rates are like less than 0.5% for most of them. It's really just not very good at all. But it's free money, so what can you say? 6% interest. And let's say we've got 2 years. We got this money. It's kind of found money. We scratch off, got $2,500, and we got 2 more years before we graduate. We want to have see what we can get out of that to buy ourselves a graduation present when we graduate from college. So interest for 2 years. Quarterly. So there's the situation. Let's find out how much the account is worth. So that's P, that's R, that's T. Quarterly means that N is 4. Okay, so those things are what we're finding from that word problem. So account worth, 2,500, parentheses 1 plus R. It's 6%, but we want to convert that into a decimal. What's the decimal for 6%? 0.06 over N, so it's 4 on the bottom. The exponent is n times t, always. So 4 times 2 there. So we're just cranking out that work there. I'm not even going to do it by hand. I'm going to do it with calculator. 2,500 parentheses 1 plus 0.0626 divided by 4. Close the parentheses. Raised to the 4 times 2. I'm just going to go ahead and put 8 there because I can do that math in my head. And we will, at the end of the 2 years, we will have gained $316.23 by doing absolutely nothing. I paid the electric bill for a month, right? That's pretty good, I think. We started with 2,500. Take 2,500 away from $2,816.23. That's where. This is what the account has in it at the end of that time. We can choose to pull it out at that time or leave it in there. But we gained, subtract away our principal investment. We gained a 316 out of that by just doing nothing, by putting that money there and not touching it. Now, that's if you don't put any other money in there. If you change the account balance by posting money to that account, then that's going to change the formula. It's going to account for a different principal investment for the next time around through there. So this is just putting $2,500 in it and forgetting about it, and coming back in 2 years and saying, "Hey, how much money I got?" And they write you a cashier check for that. Or transfer that over your checking account.
That's how we make money, Dave.
Yeah, yeah, it is. It was a wonderful time. If you had the extra cash laying around, a lot of people got up their net value by investing in savings accounts and things. It doesn't happen anymore. Can't make yourself rich now. So 28. They still do savings bonds. My wife's got some that haven't matured yet, but she's got as Christmas gifts while she was a teenager in the late 90s, early 2000s. So we're waiting on those to mature so I can buy a banjo or something. No, I'll get killed if I do that. She'd die if I took her money and bought a banjo. Yeah. But yeah, she's a piano player. I don't think she's much of a banjo player. She tolerates my bluegrass kicks here. All right, so here's an application of this. Let's say that we have some sort of we know we're going to have a need for $15,000. So me and this cable are not going to get along today. I'm just going to leave it unplugged. Surely I can get through the 3 examples. All right, so how much should we invest to have $15,000 after 4 years in an account that draws 3% monthly? How much do we invest? What are we looking for from our formula? Our formula, remember, P parentheses 1 plus R over N to the NT. What part do we not have? The principal investment. We don't know how much money to put in there. We know we want to end up with this amount, with $15,000 at the end. We don't know how much to put in at the beginning. So let's say we want to end up with $15,000. We've got this account that we know of that's drawing 3% monthly, but we want to know how much do we need to move out of maybe our larger nest egg and into this account to gain that percentage. Maybe that's a higher percentage than what my other account gains, and I need $15,000 more to pay off. I know my note on my house I'm gonna need $15,000 to pay it off in 4 years. That would put me over the top. Or maybe there's a remodel project I'm gonna do. I know in 4 years, and maybe it's the kitchen. That's how we got about $15,000. Kitchens cost that much. Yeah. So we plug in the $15,000 for the account worth. We don't know the principal amount, but we know everything else. We know the rate is 0.03. We know it's compounding how many times a year? 12 times a year. So that's 12 times 4 years out of that. What is this stuff here? Is that a variable or is that a number? It's going to be a number. It's going to be an ugly decimal number, but it's a number, right? So it's P times a number is equal to 15,000. So what do I have to do to get P by itself? Figure out what this number is and do what? Divide it to the other side, and that's going to get me my principal investment out of that. Okay? So let's find out what that number is. So 1 plus 0.03 divided by 12. And then I'm raising that, raising that to the 12 times 4 power, which is the 48th power. I'm just going to write that as 1.0025 to the 48th power times P. Because I don't want to round that until at the end. Now you don't round until the very end. Divide by that 1.0025 to the 48th power. So 15,000 divided by 1.0025 raised to the 48th power. I need to invest $13,305.80 to make sure I get $15,000 in 4 years. Have $15,000 laying there in 4 years. Or maybe I want to put that money away and buy my kid a car in 4 years, something like that. Maybe that's what I'm doing. That seems about right. My parents never spent that much money on my cars, but I hope that I can do that. I don't think I could, but I'd love it if I could. So principal investment should be $13,305.80. Again, I'm rounding up to the nearest cent. Keep in mind that the bank is never going to round up. They're always going to round down and keep the change when they're giving you money. When you owe them money, they're going to round up. Always. Good business practice in their mind's eye. Okay. That's right. I ain't against nobody trying to make $1. As long as you ain't slinging dope and cheating people. All right. This formula is for continuous interest. Compounded, the word problem might say compounded continuously. Instead of saying monthly or quarterly, they'll say continuously. And what that means is every second or every half second or every quarter of a second, the interest is dumping back into the account. It's continuous. What they've done there is, I was going through the end could be 12 for monthly, could be 365 for daily. You can keep going down into the seconds. The closer you get to infinity times a year, the closer it gets to this formula. So this formula is like an infinite number of times in is what this formula is. That E is a number on your calculator. So let's look at a problem that says, we invest let's just do $1,000 at 2% compounded continuously for 12 years. No idea what letter wrong. Oh, donut. So we invest $1,000 at 2% compounded continuously for 12 years. So we're going to plug that into the continuous interest formula. So PERT is the way I always remember that. Okay, I'll give you these formulas on the test in a couple of weeks. I'll give you the compound interest and this formula so that you'll know those. You'll have them on your notes for the Canvas stuff and for labs, so it's not a big deal. So plugging that stuff in, we got $1,000 for the principal. E to the R for 0.02 times 12. And we're working that out. So on the calculator, to get that to work out, you're going to do 1,000 for the principal times E. The E on your calculator is down the left-hand side. If you look down the left-hand side, right beside the number 4, there's an LN button. You're going to hit second LN, and that gets you the E. That's the exponential number. It's kind of like pi. It's used enough that it has its own symbol. It's E to the first power is about 2.71 and some change. It's about what it is. But it's like pi. It's used enough. You just have a letter to represent it. So E to the RT, so 0.02 times 12. Crank that out. So at the end of 12 years, at 2% compounded continuously, we have $1,271.25. $1,271.25. $271 for nothing. That's pretty good. But 12 years to get there. Hopefully, we put some more money in there during that time out of that. So that's if you ever study personal finance, which we teach in the high school now. I'm about to start teaching that to some students this next 9 weeks. Consistent, steady growth with consistent giving to yourself is how you gain money. That's hard to do. It's not easy. So y'all know how to making ends meet is sometimes harder than in some months than others. So, but if you can set up just whatever small amount you could save every month and put that in, the compounded interest, the exponential factor of it, that's going to grow over time. And it may not seem like $5 a week is much to put in there, but $5 a week times 52, and you're saving $250, $260 a year, and over 30 years that adds up to a lot. But then you add in the interest from your savings account, it adds up even faster. So that can be good for you. So next week we'll have labs at the beginning. We will cover R6. If you do somewhere around number 39 through 72, if you do R7, somewhere around 1 through 68 of those. 1.6, 35 through 76 will be good. 4.2 is the last thing we did. There's 100 problems in there, that section that you can pick from. Don't do all of them. But do some of those to get you ready for your Canvas quiz. Canvas quiz is out there for those 4 sections. It's got 66 problems on it. It's a lot, but some of them are those just 49 to the 1/3 power, stuff like that you can just type into the calculator and you got an answer. That sort of thing. So some of them are that. So that's some really short ones on there. Not as many of the really tough equations as you probably wish there were. But there's some of those on there, but not many. Okay, so labs next week, and then lecture, and then the next week is labs and tests. Okay, so 2 weeks, and then test, and then 2 more weeks, and then a test, and then final is 2 weeks after that. Okay. You guys have a great week. Email me if you got questions. Don't